let's start with a numerical problem. Let's say I have a polynomial okay, it could be bigger, but okay, let's say I have a polynomial, okay, and let's say we are multiplying it to another polynomial. Let's have okay, yeah, calculate the result. Okay, and let's have the answer. The answer is W
W raised to 5.
W raised to 5. Oh yes, okay. W raised to 5
Minus 4 omega raised to 4.
minus 4 W raised to 4
Plus 6 W square.
plus 6 W square. Oh, there is no W cube? Okay. Okay, go ahead.
7W.
Plus 7W plus 2. Is that the answer? Okay. Did you notice anything interesting while doing this? Okay, here's the interesting thing. You actually performed a convolution.
Spreading each of the first bracket with respect to second bracket.
Yes, correct, because if you, so think of this, the coefficients as a signal. It's a very odd thought. Think of the coefficients as a signal. Okay, so 2, 3, 2, minus 1 are the coefficients, and the indices or the places of the signal are actually the order of the polynomial variable. Okay, so 2, 3, 2, minus 1, and so this is the coefficient for W raised to 0, this is the coefficient for W raised to 1, this is the coefficient for W square, this is the coefficient for W cube. And so what will happen, you have this 1 plus 2W minus 1W square. Now if you just consider how that interacts with, say, this fellow 2, what happens is it actually spreads W0, W raised to 0 into W raised to 0, W raised to 1 and W square with the multipliers 1 and 2 and minus 1, correct? And so that becomes 2 plus 4W minus 2W square. So this is the spread. This is the scatter, right? Similarly, 3W raised to 1, there is already a W here. So now that will go into W and W square and W cube. And you will get the same multipliers. And so it's a convolution. Correct? Right? And so you get that answer that you get, 2 and 7. And so this answer that you get here, 6, 0, minus 4 and 1 is the answer indexed by the same W orders. Okay? So this synthetic multiplication of polynomials can be performed using convolution. Okay? There is an observation right now. You can also think of it from the gathering perspective. So if you imagine that how will the W square coefficient come about? Okay. How will the W square coefficient come about? It will have to be W square multiplied by 1 plus, sorry, which means 2 multiplied by 1, then 3 multiplied by this 2, and this 2 multiplied by this minus 1. So while gathering you get a flip. Do you see that? Okay. So polynomial multiplication is convolution. We are going to utilize this observation in rather fantastical ways in a while. Let us for a moment leave this apart and talk about the idea of a causal convolution or a causal filter. A causal filter, causal convolution filter, is something that has a rule that looks like this, which means that it gathers information only from the past and at most the present. The idea of causality only applies in time. So we are talking about time-based signals today. Okay. And what are we saying? A filter, by the way, now I can call a convolution a filter. I'll use those words interchangeably. When I say filter, I mean convolution rule. So a filter is called a causal filter if it gathers information from the current index and previous indexes, but not future indexes, right? This is the gather picture. For the same thing, what does the scatter picture look like? It looks like this. Yes. Okay. Now this is not anti-causal. This is just another picture of the same thing. This is also called causal. What you are saying is a particular input only affects the present and future outputs. Okay. So something affects only the future is just another way of saying something is affected only by the past. So these are two ways of thinking about causal filters. The idea of causal filters is understood? Okay. We will have another idea, and that is going to be an idea of a signal that has a finite start in time, or that has a start at a particular location in time. Okay. So that means that, so these are still in principle signals which are by infinite, and you will see why we need them to be by infinite, but they have zeros on the left of a certain boundary, and then non-zero numbers start occurring only after a certain boundary. And just for the sake of convention, we'll say that the index where they are allowed to become non-zero is the zero index. So all negative time indices have to be 0. Okay. We will call such signals jump start signals. Okay. Because they are 0, 0, 0, 0, 0, and they start with a jump. So they are jump start signals.
Is that an actual term or you created it?
That one is not an actual term, as you can clearly understand. This is pulled from the same hat as anthills and other things came from. The textbook term is causal signal, and I don't like that. because there's nothing causal about a signal itself being 0 in the past and having non-zero values in the present and the future. That's not causality. Causality is about functions. So
You could say that the spreading rule create, like the signal thought of as a spreading rule is causal or something.
yes, you could say that, but then signals are essentially different, right? So, yeah. So, jumpstart signals and causal convolutions. Okay. Now, tell me something very easy. If a causal convolution encounters a jumpstart signal, what will it produce?
Jumpstart signal.
A jumpstart signal. Okay? Is that okay? So, non-zero values will start only from here onwards. Okay? So, like a very simple theorem, but it's going to be useful to us in a moment. And that's why these three things kind of go together in a sense. A jumpstart signal operated upon by a causal convolution will produce a jumpstart signal. Its values before the jumpstart index will all be 0. Okay? One of the reasons we are interested in causal convolutions is because sometimes we are interested in the concept of real-time signal processing, where as the signal is coming in, you are processing it and producing the output index by index or sample by sample. Okay? If that is the kind of application you are interested in, then you cannot have a convolution that breaks causality, right? A convolution that breaks causality will require, to produce a particular output, will require information from the past and the future of that output. Okay? So, in real-time applications or what is called online applications, this will not be possible. So, the reason, one of the important reasons why we study the subset of causal convolutions or causal signal processing is because they allow us to do online implementations, where your signal is coming in and as soon as a particular sample comes in, you can produce the output for that sample. Okay? So, now I am going to give you another example. Let's say we have a causal convolution. Let's say it's this one. Okay? And let's say that the input is a jumpstart input. Except I don't know what the input is. Okay? This is the jumpstart index. So, then I happen to know that everything to the left is 0. But from the jumpstart index onwards, I don't know what the input is. Now, the output will also have to have zeros here, right? It will have to be a jumpstart output. Let's say that I know the output, and the output is this 2, 7, 7, 1, 3, 10, and then back to 0, 0, 0. Okay? So, this 2 occurs at the jumpstart index, the 0 index, and then some other numbers occur, and then again it goes back to 0. I don't know what the inputs are. The question is, can you calculate the inputs? Calculate them. So is this what we got? 2, 3, 1, minus 1, 5, and then zeros. Is this what we got? Okay. So what did we do here? It's easy to see, we already knew this 0 here, correct? And so this 2 must be 0 times 2 plus the unknown times 1, and there's only one unknown there, and so that unknown must be 2, correct? Now we know the 2. So this 7 must be 2 times 2 plus an unknown times 1, and then you get that unknown. And then you get the next unknown and so forth. Okay? That's how we solve it. This is actually just Gaussian elimination. Okay? So this is how we solved it. But this is Gaussian elimination of this matrix. But we are going to take a different outlook of what we just did. Okay? So it's okay. The Gaussian elimination part won't be that important. So if you are wondering about it, you can stop wondering about it. It's just homework problem, just for fun. How is this the same as Gaussian elimination? Don't have to worry about it. Okay, let's go ahead. Now we'll take a slightly different approach to understanding what we just did. Think of it as this thing. Think of it as a procedure where this, okay, 2, 7, 7, 1, 3, 10, and then zeros was the input, and then it produced some output here, right? We already knew these are zeros, and then it produced outputs here. That's what we did, right? We looked at these numbers and produced these numbers. These numbers are those, and these numbers are these, right? So now the question is, how did we produce these numbers? Can you, just like we have like some sort of a network diagram or like an ant diagram there, is there some kind of a diagram here?
Can we not just flip the arrows to get the outcome?
Something like that, something like that.
In a minus.
Try to draw a network diagram here. Okay, here we go. Somehow this 2 gave 2, okay? We'll come back to how this 2 gave this 2 in a moment. Now, we want to produce the output here. Let's look at how we produce this 3. It was, so what we said is that the contribution of this 2 is 2 times 2 is 4. If we subtract that contribution from this 7, what remains must be this 3. Okay? And so, what we where is that 2? Here on this diagram. It's here. Okay? And so what we did is this, multiplied this by minus 2 and multiplied this by 1 and added them together. to produce 7 minus 4 is 3. Correct? Let's see if it keeps on working. The same thing. Now multiply this by minus 2 and this by 1. And what do you get? 7 minus 6 is 1. Correct? Sorry, something wrong happened. What wrong happened? Is 1, right? Is 1. Okay. So 1 multiplied by minus 2 is minus 2, plus 1 is minus 1. Minus 1 multiplied by, right? This is what we did. Minus 1 multiplied by minus 2 is 2, plus 3 is 5. 5 multiplied by minus 2 is minus 10, plus 10 is 0. And then of course everything is 0, so we'll keep on getting 0 after that. Correct? Is okay? Where did this 2 come from? It's the same thing. We multiplied this 0 by minus 2 and then added the 2 and we got this 2. Right? Just a different way of saying, hey, I know this is 0, so there's no contribution from here, so this 2 must have entirely come from here. Make sense? And so if you think about it, what do we actually have? We have a structure which is a new kind of structure. It's not the same as before. It's a new kind of structure. It's a structure that looks like this. Structure that looks like this. But then that structure goes on stepping across time. Okay? And that's a new kind of mathematical structure that we have created. Is okay? It's a, right? Now, this new mathematical structure that we have created, let us try to understand the properties of this mathematical structure. For the time being, forget that it came out of some other structure. It came out of our need to invert something, the effects of something. Let's forget that and just think of this itself, whatever it is. It's an operation. Let's try to understand that thing itself. Okay? My one question is this structure shift invariant? Right? It's the same structure. Forget the jump startness of the signal. We actually need the jump startness to do the inversion. Otherwise, you can't start. We need the jump startness for the 0 here. Okay, by the way, that's where the jump startness is useful to us. Forget the jump startness. You can shift this signal any way you want to, and then the output will shift, correct? Equivalently. Is that right? Right? So this structure is a shift invariant structure. What's the next question we might ask? Is this a linear structure? Is this a linear structure?
Yes.
It is, and there are more than one ways of convincing ourselves. One way is as follows. You think of it as, so this structure is the inverse of this structure, right? Now, the inverses of linear operations, if they exist, are linear. You might know some linear algebra which says that. If you know that, well and good. Otherwise, it's actually easy to see. What is linearity? Let's just do scale invariance, okay? Scale homogeneity. If the input became 2 times, what will happen to the output? It will become twice as big. It will become 2 times, right? Now, if you're thinking about the inverse, if the output becomes 2 times, what must be the corresponding input? No, must be twice as big, because that's the input that produces the output. And if the inverse exists, that means that the input for a corresponding output is unique. Correct? And so the inverse has to be scale invariant. In a similar manner, you work it out, you will see that the inverse also has to have superposition. So the inverse has to be linear. Okay? That's one way of convincing yourself that the inverse has to be linear. Another way to convince yourself is just directly, for example, you can just work with this, right? What happens if all these numbers become 2 times? If all these numbers become 2 times, then this fellow will become 2 times. If this fellow becomes 2 times, then all the inputs for this fellow become 2 times, which means this fellow becomes 2 times. That makes this fellow 2 times, that makes it, so forth. So the output will become 2 times. The same thing you can do with superposition as well, and see that, just mechanistically see that you get superposition, which means that this operation is linear. If this is linear and shift invariant, what does that mean? It's a convolution. It's a convolution. Why does it look different?
It doesn't look different. I mean,
It
it's just a
only
rule.
looks different, but isn't different.
It's
Because
a rule, right? So, why is it different?
Let's here's a different way of looking at my question. Why doesn't it have the convolution lines that we expect? That's the point. We haven't found the convolution lines. So my next question is, find the convolution lines.
Can I make a guess?
Make a guess.
This is like composing 1 minus 2 a lot of times. Like the convolution minus 2 1. Like the gathering rule minus 2 1 many times.
Something like that. What are the convolution lines is the question.
So, like this, just representing it in this format. Is that what you're asking?
Yeah.
Okay.
One down and minus 2 from all the previous indices.
Yes.
1 down and minus 2 from all the previous indices.
Not from all. Just like the.
Just like the first one. 1 and minus 2 from here. That's it. Okay. He's saying all. He's like going overboard. Like all.
I tried calculating, but I think it's fine. I think it's the last. Just one before that.
He tried calculating it, but he couldn't reach all, so it cannot be all. Okay. Remember, the convolution rule is also the impulse response. So if I ask you what is the convolution rule of this thing, just calculate the impulse response. Do it.
GP with rule like the ratio minus 2.
Yes. And so what do we get? We get that if I put in this, right, the impulse input 1 0 0 0 0 0, you have to see what is the output that we get. And the output that we get is, this bit gives 1. Now this is 0, but I get a minus 2 from here, so it gives minus 2. Now minus 2 times minus 2 is 4. 4 times minus 2 is minus 8. Minus 8 times minus 2 is 16. Minus 32, and so forth. Okay. This is the impulse response. And so this is the convolution rule. It is a convolution. Okay. If you take this, you can think of this as a convolution. If you take that convolution and you put it as a spreading rule, 1, minus 2, 4 and so forth. Okay. And you go through this signal, you will get back the signal above. No doubt about it. And we have proved that. Okay. Just, it's infinite, but it doesn't trouble us actually, because if you look at the gather version of this, what is happening is you are getting a infinite gathering, but you have only finitely many non-zeros here. So it doesn't matter. You get some numbers, and then it starts becoming 0 after that. Okay. Is it okay?
But why the termination is needed?
Which
On
termination?
On the right hand side. Zeros after a point.
No, they will come about. I mean, these zeros?
Can you repeat what you said?
If you took this thing that we found, this 1, minus 2, 4, minus 8 rule, infinite rule, and if you just scraped it along and calculate the outputs, you will get these numbers and these zeros as well.
Because the input, like the initial signal had zeros.
Because
Is that the spreading?
Because there were zeros in the top signal, that is why we will get zeros.
Yeah, yes, okay. Yes, that's true. We are getting the top signal back, yes.
Yeah, I thought there was some problem with this being infinite.
There will not be.
Yeah.
Is that the spreading rule or the gathering rule?
This now is the gathering rule. I flipped it around, so it is the gathering rule. Right, this is going to the right, I am putting this on the left, so I flipped it around, so it's the gathering rule. I first showed the spreading rule, then I showed the gathering rule. Okay?
So for an arbitrary point whose input index is 0.
For
For a point whose input index is 0, but all the arrows come from non-zero indices, we expect plus and minus to cancel out. Like since we have infinite arrows on the left, this 2 will also go to some infinite position forward, right? When we convolve.
yes,
And all these other numbers will
not infinite, but yeah, any large position it will go to. There is no such thing as infinite position. Yes, yes. Yeah, you can prove that, yes. Yeah. And yeah, do it at home, but yes, that is correct. That is what will happen. Okay? So now as you see, this structure is a certain kind of structure. It's a special case of what is called infinite impulse response filters. Okay? This structure is a convolution filter, and it's a special case of what is called infinite impulse response filters. Okay? This specific kind of filter which takes in previous outputs and multiplies them is called an autoregressive filter. Autoregressive filter, or AR filter for short. Okay?
Could you repeat the definition of autoregressive?
Autoregressive filter is a filter that takes one number from above and then all other numbers from its own previous outputs. Okay?
What is AR?
AR is autoregressive. So by the way, if I had 3 lines here, let us say, I had a third line here, what would be the corresponding structure which is the inverse structure? It would have 1, -2 and -5. Do you understand this? If this was 1, 2 and 5, then the corresponding inverse structure would be 1, -2 and -5. Okay? So in general, autoregressive filters can have lots of lines going to the left. And then they are sweeping in time. Okay? Question?
Yeah, I mean, I was thinking, how is this related to autoregressive model?
It's the same thing.
Yeah. So it is.
Yeah. So, if you like quantitative finance, anyone does like shares, derivative trading, whatever, autoregressive, same autoregressive.
Oh, so we know how to do stock market.
Now you know how to do stock market trading, please don't.
Investments are subject to market.
Okay. So by the way, people who call this autoregressive tend to call this MA, which stands for moving average. Again, derivative and stock market traders like this, moving average, autoregressive. Did you think I would suddenly be teaching you quantitative finance? You didn't. It seems I am. Anyway. Basically, stock market prediction is all signals, right? Signals. We will have been doing signal processing. You have no better models, you try to use an ARMA model. See what happens. Try to predict it to the future. Hey. Anyway. ठीक है? If I were to take this structure, the 1 and -2 structure, and cascade it below this structure, what will I get? What will be the composed operation? It will be the identity operation. Agreed? Because these two are inverses of each other. Right? It's the identity operation. What is its impulse response?
Just a single one.
That's just the single one, right? The impulse is the impulse response. Right? The Kronecker delta 0, 0, 0, 1, 0, 0, 0 is the impulse response of this composed operation. Okay? Now, what did we learn? That so this is 1, 2, right? The spread is 1 and 2. Let's write this like this: 1 plus 2W. Okay? And then there is, so let me call this F, let me call this G. There will be some, okay, let's say cursive letter G, which is a polynomial in G. I don't know what it is, something in G. Okay. These two polynomials are multiplying. Why? Because polynomial multiplication is the same as convolution. And why are these two things convolving? Because cascading of filters convolves their impulse responses. Agreed? So this must produce a polynomial which equals or which represents the cascade of the two. But the cascade of the two is what? Just that single one line, right? The identity convolution. And what is the polynomial representation of that? 1 plus 0w plus 0w square. 1. Correct? Yes? Correct? And then what's g of w?
Minus 2 omega plus 1.
Yeah, but I mean, yes. But that's a simpler thing as well, right? I mean, this has to be true, right? I mean, yes? This has to be true, correct? I mean, otherwise everything we learned from 7th standard onwards is a lie. If I can't go from here to here. Okay? But the same GW has to represent the impulse response as well. And what was the impulse response? 1, minus 2, 4, minus 8, 16, minus 32. Correct? So this has to be 1 minus 2w plus 4w square minus 8w cube and so forth. What? 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 Are these two things the same?
Yes. Yes.
Yes, they are. One of them is the Taylor series of the other.
Or you can think that the sum of the GP is that.
Yeah. Geometric series. I mean, it turned out to be geometric series in this case, so it's easy to see. But if you had like multiple lines going, the geometric series formulation will go. If you had like that 5 and other things and you are doing all of that in a more complicated situation, that will go. But still you will get these two things coming out, and one of them will be the Taylor series of the other. Okay? So there's multiple ways of thinking about this now. You can think of this as a shorthand of writing this. And equivalently, you can think of this structure as a shorthand way of implementing a convolution with these numbers. Okay? This is the very interesting thing about an autoregressive filter as an infinite impulse response filter. The interesting thing is that it has got an infinite impulse response, but it has got a finite implementation. Right? The reason this structure is so interesting is because in a finite implementation with a finitely many additions and multiplications, you get the benefit of a convolution which has an infinite impulse response. Okay? In a finitely many, so this structure, the structure which is actually autoregressive, okay? This structure gives you the benefit of convolving with an infinite impulse response using only a finitely many additions and multiplications. Okay? So that's what an autoregressive filter is. It uses an input value and its own output values. Okay?
Technically, we are not using finite denominator because our output is infinite.
Yes, yes. We are using an infinitely many. Why? Because an effect of infinitely many past input samples is present in the just previous sample. You keep on accumulating the effects in your outputs and reusing them, reusing them, reusing them. Right? Which is how by using outputs instead of inputs, you get the benefit of using infinitely many inputs. Okay? To give you a very simple example, if you know, okay, let us say you want to calculate your lifetime income. Okay? You are all looking stunned because you are still students, but let us say, imagine into the future, one day, you wanted to calculate your lifetime income. Now, if you knew your lifetime income till last year, and you want to calculate the lifetime income till this year, what will you have to do?
Lifetime income is till now whatever.
Lifetime income. जिंदगी में क्या मैंने किया, क्या हासिल किया? Yes. Let's say you already have the difference only with you, so you don't have to worry about all of that. Let's say you have zero spending. Chalo, I'll make the problem simple. Zero spending. अभी तो जीरो ही होगा ना, इनकम नहीं है, स्पेंडिंग का.
Spending will be there, na? There is no income and spending हो रहा है.
Let us say you are like that. Anyway, chalo, it's an artificial problem. This is just for fun. So you have, if you know, correct. If you have the lifetime income till last year, and you want the lifetime income till this year, all you have to do is add the lifetime income till last year to the income of this year. And that's an autoregressive operation because you took the lifetime income till last year and added it to the income this year to get the summation, infinite summation of yearly incomes for all previous years. Right? So as a moving average, it's a 1, 1, 1, 1, 1, 1, 1, 1. As autoregressive, it is just 1 and 1. Okay? Sorry, this is Udayan Kanade right to call it moving average, but the impulse response is 1, 1, 1, 1, 1. Okay? So these two are the same, and that is happening in generality in what we learned right now.
You can think of compound interest as an autoregressive operation.
Yes, with a single impulse being the initial withdrawal of money. Yes. Okay. So now autoregressive, if you think about it, uses only one input and as many previous outputs as you want. Okay. Moving average uses as many previous outputs and as many previous inputs and current inputs, but is not allowed to use outputs. Okay. In general, what can you think of would be a generalization and still implementable in a finite computation structure.
Assuming finite input.
You are not actually making any assumptions about the input. Kickstart input. No, what were you calling it? Jumpstart input. Jumpstart input. My question once again.
Yeah, question.
You can think of f and g as signals and just compose them, right?
You can think of f and g as signals and compose them. Yes. So now, okay. Let me ask the question more specifically. Forget that g is the inverse of f. Just think of autoregressive structures as a kind of convolutional filter. Okay? Think of moving average as another kind of convolutional structure. Moving average does what? It takes a weighted sum of the present and the past inputs. Autoregressive does what? It takes a weighted sum of the present input and the past outputs. Can you think of some structure which generalizes both of these? Forget that one of them can do the inverse of the other. Forget that for the moment.
Is it from something that we have already learned before?
No. Or yes.
I have an answer, but I don't think it's related like to what has been taught.
Takes the input from the present input. It takes information from present input and past inputs and outputs.
Yes. So you correct. So the generalization is, was that your answer as well? Yeah. Okay. Yeah or no? Okay. So the generalization is a filter. Generalization is a filter which takes information from the present input, the past inputs and the past outputs to produce the present output. Okay? So yes, we'll see that in a moment. So it's something that looks like this. Okay? Yes? And this structure is going to move along, move along, move along, move along, move along. Okay? Now, by the way, when I say this, these lines and these lines don't have to implement an inverse of each other, okay? In fact, if they are implementing inverse of each other, they are just cancelling out. Then there's no reason to be doing this strange natak. They are not. These lines and these lines are now doing some totally different things. Okay, but this is a generalization. Now, this filter is called an ARMA filter.
Autoregressive.
What was the point of using this?
We don't know the point yet.
But what was motivating the use of?
Nothing yet. Motivation will come. Okay? Now, as he rightly pointed out, so right now what is this? This is just something, right? I mean, just a procedure. Just a procedure. Okay, we don't even know what it is. The motivation currently was purely mathematical. Could we come up with some structure which is a finite structure of which both moving average and autoregressive are special cases? That was the purely mathematical motivation from which we have created this right now. Okay? That's the only motivation we have right now. Okay. Now, the question is this a convolution? And is this a convolution? Yes. And why?
Shift
Again,
invariant.
Shift invariant.
Shift invariant and linear. Or there's another interesting way that he pointed out earlier. You can actually think of this structure as a cascade of a moving average structure and an autoregressive structure. Okay? So, this is equivalent to take those moving average numbers, put them here, take those autoregressive numbers, put them here, and then you have to add this line and put in a multiplier of 1. Okay? Is it okay? Do you see that this and this produce the same result?
You can put one either of the one.
I'll come to that in a moment. Okay? Now, this is a moving average, so it's a convolution. This is autoregressive, so it's a convolution. the cascade of two convolutions has to be a convolution, which means this has to be a convolution. And so we got a more general structure called an ARMA filter, which can be implemented in a finite number of multiplications and additions and is a convolution. Okay? So here's the interesting thing about this one here. When you're talking about ARMA filters, you can always fix this number to 1. And why is that? If I had this number to be 2, let us say, should be allowed, right? When I'm talking about autoregressive filters, that label could be anything. Because to invert that correctly, you could require some other multiplier.
You can just distribute that in other.
Exactly. You can distribute this 2 into these numbers here and then just call this 1. So without loss of generality, you can always label this line with the multiplier 1 when you are talking about ARMA filter structures. Okay? What will happen if I switch these places? Which means these numbers I put here above and then these numbers I put below. What will this be? It will be the same thing. Why?
H star G is C star.
Commutativity of convolution. Okay. But these are two very different implementations. Okay. Just think about it. Here, now, okay, imagine yourself to be a signal processor, which means you are an actual chip. Okay. Or if you go way back into history, you are a human being employed by some scientist who is actually doing signal processing. Every day a new number comes in and you multiply it to something. Imagine you are a chip and you want to implement this. How will you implement it? Input is streaming in. Okay, you are just getting, all you are getting is the number now. And sometime later you again get the number now. You get the number now. You get the number now. All you are getting is the number right now. How do you implement this? You will have to remember a finitely many past input numbers, right? You'll have to store them somewhere. And as the next number comes in, you shift everything. As the next number comes in, you shift everything. Okay? Is that okay? This breakdancing structure is called a queue in computing terms, right? Put in a new number, shift everything. Putting in a new number, shift everything. So you shift everything. Similarly, you will have to remember all of these past numbers as well, which are in your previous outputs. So you have to remember a few inputs, a few outputs, and as the next number comes in, you shift, you shift, you shift, you shift, you shift. Okay? In implementing this, what do you have to do?
Stacks.
No, it's still a queue. But the interesting thing is that,
The middle one that needs to be done.
yes, you have to remember this middle one. It's odd. It corresponds to neither the input nor the output. But it's, you remember just this line and shift it back, so you need less memory. When the first signal processing people came about, they had like memories of 5 or 6 registers, so they were really enamored by this one. Okay, so this is called a type 1 implementation of an ARMA filter. This is called a type 2 implementation of an ARMA filter. They are mathematically equivalent, but this one uses lesser memory than that. Type 2 uses lesser memory than type 1. Yes. But type 1 looks more like the bare ARMA filter that we imagine. Let's do one interesting thing and then we'll take a short break. What is the inverse of an ARMA filter?
Type 1.
No, doesn't matter. No? Now I'm talking about inverse as a mathematical. Type 1, type 2 is just an implementation detail, right?
What's our ARMA filter is ARMA.
Inverse of an ARMA filter is an ARMA filter. You see that? Because the inverse of an AR is MA, inverse of an MA is AR. So the inverse of an ARMA filter is another ARMA filter. Isn't that brilliant? What is the W polynomial representation of an ARMA filter?
That's the spreading rule of, like, imagining this as a convolution and then finding the spreading rule.
It's better to use the type 2 this thing for
No.
imagining.
Is it? Type 1 or type 2 doesn't matter actually. See, it's simple. What is the W polynomial representation of this, the MA part? It's just some polynomial, correct? Like, I don't know, some 3 plus 2W plus 5W square, let us say. Okay? What is the W polynomial representation of this? It's actually, I'm calling it polynomial still, but it's not actually polynomials. They are functions, so let's call them W functions. What is the W function representation of the AR filter itself?
1 in the lower part.
1 by a polynomial.
It is going to be 1 by a polynomial, right? Why? Because its inverse is MA, which is a polynomial. So the AR is going to be 1 by a polynomial. Okay. To be very specific, if this has numbers like -2, let's say -2, 4 and -3, what is the polynomial representation? Its inverse has numbers 1, 2, -4 and 3. Correct? Yes? And so the inverse has the representation 1 plus 2W, sorry, minus 4W square plus 3W cube, and the reciprocal of this is the W representation of this autoregressive filter, correct?
So if we take the Taylor series of this polynomial, it will be the same thing.
Taylor series of the reciprocal of this polynomial. Then you will get the infinite impulse response of this thing. Yes? And it will have a, right? It will keep on ringing. If you forgot this and just gave this an impulse input, it will keep on ringing. It will have an infinite impulse response. Okay. So now, what is the W representation of both of these cascaded to each other? It's just the multiplication of the two, which means you have to take this and just divide by 1 plus 2W minus 4W square plus 3W cube. This is the W representation of the ARMA filter.
Let's see F into G.
Right? Yes. What is the inverse of this ARMA filter? It's an ARMA filter. What is the W representation of that? Just the reciprocal of this. Okay? This much is okay? I'm going to ask you another slightly stranger question. Suppose I have two ARMA filters. Two ARMA filters. This is one ARMA filter, this is another ARMA filter. An input is coming in. The same numbers go to two ARMA filters. The output gets added together and I get one output. Is it okay? Same input goes to two filters and I get an output. Okay. So two parallel convolutions. Okay. For the moment, forget if they are ARMA or anything. Is this structure shift invariant? Yes. Is this structure linear? Yes. So this is going to be a convolution? Yes. Now the question is, if this is an ARMA filter, it has got a W representation which is some polynomial upon polynomial, what's called a rational function, by the way, if you remember. Rational function. This is an ARMA filter, it is a rational function. Then what is the W representation of the combined thing, which must be a convolution, which means it must have an impulse response. Since both of them are causal, it must be causal, which means it must have a W representation. What is the W representation?
Sum of the addition.
The sum of the two W representations, right? And let's see why. Let's see why. Because if you just forget this for a moment and take the Taylor series, that Taylor series actually gives you the impulse response of this. The Taylor series of this thing gives you the impulse response of this. The impulse response of this whole structure is just the sum of these two impulse responses. Now, what is the W function whose Taylor series is the sum of these two impulses? It has to be the sum of the two W functions, right? Which means what you have to do is take this and then add something else, something plus something W plus something and so forth, and something. You add these two together, and that must be the W representation of the of two ARMA filters on two parallel paths. But now what can I do? Addition of two rational functions is a rational function, right? You remember, I take the denominator, multiply here, take the denominator, multiply here, multiply denominators, add the numerators. So, summation of two rational functions becomes a rational function. So then what did we just prove?
Summing ARMA filters, we get an ARMA filter.
Yes, summing two ARMA filters, you get an ARMA filter. By the way, it is very hard to describe if you sum two ARMA filter. If I just showed you all the coefficients, and if I gave you all of these coefficients here, and I asked you to I told you that they are on parallel paths, I am summing them up. Okay. Tell me what is the equivalent filter structure. It would be very hard to calculate. The simplest way to calculate it is actually to use the W representation. That's the easiest way to remember. Multiply the polynomials crosswise, multiply the denominators, add the numerators, that's it. Whatever you get, and now interpret it as an ARMA filter. Okay? So, like for example, if you are standing at the crossroad of two hallways, let us say, okay, and I am speaking at another crossroad of two hallways both leading to you. Suppose this hallway had an ARMA filter representation. This other hallway had an ARMA filter representation. What is happening at your end? The two signals are being added. And now we know that this whole thing can be simulated by a single ARMA filter. Okay, this is very interesting. So ARMA filters, the structure is closed under inverting and under parallel additions. It's also closed under cascading. If you cascade two ARMA filters, what will you get? You'll get an ARMA filter. How?
I mean, it's the same as a multiple.
Yeah, you are multiplying two of these to each other, and that is going to be a rational function. Okay, so that is amazing. So lots of things you can imagine doing with ARMA filters. You do not get a larger structure. You keep on getting ARMA filters. And so this W representation becomes a shorthand tool for calculating all sorts of combinations of ARMA filters and all sorts of algorithms that you can come up with. By the way, so this W representation, your textbook calls it the Z transform or the Z transform if you are American, which you are not, but someone on YouTube one day in the future could be. So, what we are calling W, the textbook calls it Z raised to -1 for who knows what reason. Okay, textbook calls it z raised to minus 1, and then they don't actually invert the z or reciprocate the z. They will write it as 3 plus 2 z raised to minus 1 plus 5 z raised to minus 2. What are the minus signs doing? Someone came up with it first and it stuck for the last century the way it is. Okay. But what they are actually doing is using polynomials to calculate all sorts of operations with ARMA filters. ARMA filters are the most generalized, finitely implementable structure that we know, that is a convolution. We'll take a 5-minute break and come back and see applications of what we just studied. By the way, the polynomial representation gives you a lot of interesting analysis methods as well, and I'll quickly explain one to give you a flavor of how useful the polynomial representation is. So one question we might be trying to answer is an ARMA filter stable, what is called stable, okay? Which is basically, if I were to put an impulse input, I know I will get an infinite impulse response. So does this infinite impulse response die down or go on increasing? Okay, because it's going to be some kind of a geometric series kind of thing, right? And so the question of whether it dies down or maybe it goes on increasing becomes an important question from what point of view? From the point of view of, if I am going to think of the ARMA filter as a model of some real world phenomenon.
What point do you truncate it?
What point to truncate is one thing, or you should not allow its response to go on increasing more and more, right? Like what we saw here is an unstable filter. 1, minus 2, 4, minus 8, 16, minus 32, the numbers are going to go on increasing. Mathematically, nothing wrong with it. Okay? Mathematically, it's fine. But as an inverse of something else, it's also perfect. But if I were to say that this itself is the representation of some real world phenomenon, that will probably not be the case, because real world phenomenon don't have a ringing structure where the ringing goes on increasing more and more and more and more. Echoes usually die down over time, right? And so the stability question is a question. Now, if you look at moving average and autoregressive parts, what is the part where the stability actually comes into question? The autoregressive part, right? And so really we are trying to analyze whether the denominator is stable or unstable. Okay. And one simple way of doing that is going in reverse of what we saw a few minutes ago. Okay. For the time being, let's forget the numerator. Let's just look at the denominator.
Sir,
Yes.
what do you mean by stable here? I'm sorry, I didn't understand.
Stable means if you put in an impulse, it is an infinite impulse response that you will get from here onwards. Does that infinite impulse response die down over time or go on increasing over time?
Okay, so it's stable if it dies down.
Yes. It's stable if it dies down, or it's unstable. It's like doing more and more and what an unstable fellow. Okay. Okay. So you have this, and you are wondering about the stability of this autoregressive structure, correct? Now, one trick is to decompose it into things that look like this. Or it could be something else here. Okay? Do you remember this? Do you remember this? What is this called? Partial fractions. Thank you very much. Okay? Partial fractions. And We studied this in school sometime, so I will not repeat it. No. I'll give it to you as homework if you didn't study it in school. Basically, any polynomial has a decomposition into roots. Correct? Now, for that decomposition, you have to go into complex numbers, okay? So, something we avoided for the whole lecture, you have to do for this part. You can decompose it into roots. Once you have decomposed it into roots, then you can separate it out into sums. And there's like, you have to just invert, it's linear algebra actually. You have to, it's easy to do. You will see that it's easy to do. And you end up with some structure that looks like this, okay? So, this structure is what? This structure is now a lot of tiny ARMA filters in parallel to each other, correct? Because you are adding them now. Is that right? Now, when will this whole thing be stable? When each one of them is stable. Because if a single one is unstable, then that's going to blow up and all the other stability will not matter because you are adding all of them. Okay. The question of whether two of them could be unstable and cancel each other out, we'll just for the time being leave that out. That requires much more mathematical analysis, so leave it out for the time being, okay? And so the question becomes, is each of these partial fractions a stable structure? But that's easy to analyze. Why? Because now these are all order 1 polynomials, correct? And an order 1 polynomial is going to have just one line coming from here. And when will this be stable and when will it be unstable?
Greater than 1. This time.
Yes. Its absolute value is greater than or less than 1, right? If this number is between -1 and 1, it's a geometric series which will die down. If this number is has an absolute value that's greater than 1, then its geometric series will blow up. And that is your stability analysis. As a side effect, by the way, we also showed that any autoregressive function is actually a sum of geometric series always. Okay? Because each of them is a geometric series. And that becomes the basis of many estimation algorithms. If you want to estimate something as an autoregressive function, you actually estimate it as a sum of geometric series and then go the reverse, and then you get a autoregressive system as an estimate of a real world system. There are a lot of techniques which we will not go into today. I will go into some techniques today, but there are a lot of ad hoc techniques of designing filters which are based on the idea of ARMA structures. Okay, so basically these techniques go in the following way.
I had one question.
Yes, go ahead.
Here, instead of a, so we have a GP over here.
Yes, because we had only one line, so it's a geometric progression. Yes.
So if our factor was a complex number, then we will have a periodic GP again.
So when you do the decomposition, it could be a complex number, which means that this multiplier could be a complex number, and your GP could be periodic, or I mean, the output would be rotating, but it could be rotating and dying down, or rotating and blowing up.
So even in that case, we have a stable and unstable.
Yes. So yes. So if the
Periodic, what do we classify it as?
it's called metastable. Because you asked. Something whose complex number exactly has the magnitude 1 will neither die down nor blow up, and such an autoregressive structure is called a metastable autoregressive structure. They have a name for it. And I remembered it. Okay, chalo. Now, yes.
Can we always decompose polynomial of any order into its groups?
Can we always decompose polynomial of any order?
Into the product of its groups.
So, that's a very good question. Can we always decompose the reciprocal of the polynomial of any number? Oh, are you saying just a polynomial of any number into a product of order 1 terms? Yes, that is called the fundamental theorem of algebra. You can always decompose a polynomial into a product of order 1 terms. It takes me around 2 lectures to prove, but yes, that is a theorem. But it's true only for complex numbers. So you have to up-convert everything to complex numbers. We have done it 100 times. So you have to up-convert everything to complex numbers, and then it's always the case. The second question is slightly more tricky of whether that will always give you a rational, a partial function representation. That's a little bit more tricky. If you have repeated roots, then the partial fraction becomes a little bit more complicated. All of this analysis can still be done. It's slightly more complicated than what I presented right now if you have repeated roots.
So even in that case, we will be able to decompose into
Linear and
like by linear, I mean the power is not there.
you have to go to slightly non-linear or linear as in order. Higher, you have to go to higher order terms. Let's not use linear because all of this is linearity. So you have to go to higher order terms, but there are ways of figuring out the stability of those higher order terms to do it completely. But so what I presented today actually works very well as long as your roots are distinct. Okay. So by the way, just because we are here, so you have a numerator and a denominator, right, of your function of an ARMA representation. The roots of the numerator are called the zeros and the roots of the denominator are called poles. Okay. Technical term, it's in the book. And so what I am calling an ARMA filter, the book will call it a pole zero filter. Okay. What I am calling a moving average filter, the book will call it an all zero filter. What I am calling an autoregressive filter, the book will call it a all pole filter. Okay. Yes. Just to match what I am saying to the book. Yes, go ahead.
What if in ARMA, like, there are some common roots for numerator and denominator which cancel out?
That's a very strange situation. The stability analysis then gives one result. It's called pole zero cancellation. There's a whole theory about it, and there's a whole theory about it. They do cancel out. Yes, they do cancel out, but there are practical considerations which could cause a problem. So if you have a non-zero pole, cancelling if you have an unstable pole, cancelling out that unstable pole with an unstable zero may or may not work depending on exactly how you implement the convolutions. Okay. All these questions are right. So I'm happy. Shall I go ahead? Okay. So there are these like ad hoc filter design methods, and I'll just kind of indicate them. So basically, some scientist comes up, and it came up like 80 years ago, or 120 years ago. Okay, there are great names like Chebyshev and so forth, and said, "Hey, I propose 1 plus 2z upon 3 plus 4z by the z square as a filter." I propose, okay? And then that's an ARMA filter, right? And then they calculated its board plot, and I said, oh, such a nice, not I said, they said, oh, such a nice board plot, has got very even characteristics here, very close to 0 characteristics there, see, so nice, okay? So, lot of these people came about and proposed their own filters, and then a large part of your book is about how to take all of them and further combine them or put them on parallel paths or tweak them around to get even more filter structures, okay? Right? So, I mean, for example, if you want, let us say, something that has got this board plot. Board plot. It's not a not board. I'm not saying board plot. BODE, board plot. I taught board plots, didn't I? I did teach board plots. It's in not tutorial.
Main class itself.
What? It's 2 classes back.
DTFT. Just call it DTFT. The discrete term Fourier transform. Okay. So now there is this. So if I want this, right? So which means what? I want these certain frequencies and these certain frequencies. These are just the negative frequencies of the same thing, right? And that's what I want. Why do I want it? For some communications thing, something, whatever it might be. Okay. For example, color TV has got this kind of a signal. So on two bands. One of them is a different band than another. Go look it up. So is there color TV transmission anymore? Is DD still transmitting? Can an antenna still catch DD? Doordarshan? Do you know what Doordarshan is? Okay.
You know that.
No, it's
But not by cable, by the Yagi antenna.
Yagi.
That antenna. Anyway.
The one with like that antenna?
No, anyway, doesn't matter. Okay. So then it spends a lot of time saying, how do we do this? Oh, I know a filter structure which can do this. I know a filter structure which can do this. Let me add the two filters together, and then you go through all of that, take the Z transforms, add them, create a big Z transform, and then implement it as a type 1 or a type 2 filter. So all of that is a lot of just manipulations. You will be able to do it, but the book spends a lot of time teaching you all of those manipulations, okay? And the filters that were proposed by various people. Some Butterworth filters or Chebyshev filters and so forth.
This is the same guy who got the Chebyshev inequality.
I am assuming Chebyshev polynomials, Chebyshev inequality and Chebyshev filters are actually the same Chebyshev. I am assuming, but I don't really know.
What if there is their son, father and grandfather?
They could be son, father, grandfather or uncles, or they could be like who are those people?
I forgot.
Who are those people? Pascal? No.
Both.
There's actually like a lot of identities, but there's like 4 or 5 people living in one house, and they were like, ये इस bedroom में जाके ये theorem निकालता था वो. ठीक है. So by the way, if I have, let's for a moment go back to moving average polynomials. Sorry, moving average filters. If I had this 1 plus 2w minus 4w square, if I had this moving average filter, now I can just write a polynomial and say that this is a moving average filter. That's correct, okay? What is the DTFT of this filter? So remember that as a filter, this is this fellow, right? 1, 2, minus 4, correct? And so the DTFT is going to be the eigenvalue of an input which is which is rotating at omega, correct? So this is one angle minus omega, one angle minus 2 omega, and so forth, yes? And so the DTFT is the output here, because the input is 1, output is here, eigenvalue is DTFT, correct? So this output is the DTFT, and this output is 1 plus 2, 1 angle minus omega, minus 4, 1 angle minus 2 omega, correct? Now, if you know the W representation, how do you calculate the DTFT?
No.
By substituting W equal to 1 angle minus omega, okay? You just substitute it, evaluate the polynomial, and you get the DTFT.
This is the output, right? We have to scale it by input. In this case, it is 1, so it's.
So we always do that, no? We look at the output corresponding to 1.
If you don't have impulse response, then we will have to.
It's not impulse, it's a spiral input. We are calculating the eigenvalue, DTFT of a filter.
1 हमेशा होगा.
Yeah. We did all of this in a previous lecture, so look it up. Correct? So, we substitute into the W function, we substitute 1 angle minus omega, and you evaluate that. It evaluates the number, a complex number. And that is the discrete term Fourier transform. It is the eigenvalue that that particular omega spiral will suffer. Okay? So here's one connection between the W polynomials or the W functions and the discrete term Fourier transform. It sheds new light onto how come multiplication of polynomials was convolution. Because multiplication, it had to be multiplication because those polynomials have inside them the DTFT and you have to multiply DTFTs. Okay? Think about it. Now, if I take the reciprocal of this, 1 plus 2W minus 4W square, what will be the DTFT of this? What you think by pattern matching is actually going to work out. What you think by pattern matching is, hey, let me just substitute W here. That will give me a complex number and that is the DTFT. And that actually works out. Why? Because
They have to cancel each other, so their Fourier also have to cancel each other.
exactly. Since AR and MA have to cancel each other, if you are taking the reciprocal, these two have to cancel each other as processes. If they have to cancel each other as processes, their Fourier transforms have to cancel each other by multiplying. Which means that they have to be reciprocals of each other. The Fourier transforms have to be reciprocals of each other. Which means that this is substituting W equals 1 angle minus omega into this is exactly going to give you the correct answer. Okay? So, in general for ARMA filters, calculating the DTFT given their W representation is just a substitution. Okay? So, that it's a beautiful thing, the W representation, right? And at first I didn't understand. I mean, it starts with the Z transform, the book, and you're like he wants. You're like, ye kidhar se aaya sigma something e raised to minus, what is happening? And then it goes on representing everything. The beauty of the W representation or the Z transform is that simultaneously it is a computation method for all sorts of things, addition, inversion, cascade, and also easy to calculate eigenvalues of spirals from the W representation. Okay? Just a few final algorithms based on the W representation. An autoregressive filter is not necessarily just, what am I saying? So, mathematically we saw what an autoregressive filter is, and we saw that is the inverse of a moving average filter, and oh, so we like it. But is there a natural modeling reason for an autoregressive filter? Okay, like
As you said, income till present.
that's a good modeling reason, income till present, right? The accumulator or the integrator is a natural autoregressive filter. Okay, let me give you an interesting example. So I am standing here, right? And there's that back wall of the class. Okay, now if I am speaking something, what is happening to my sound?
Reflection.
Goes, comes back, and
Oh, again.
and goes again, and comes back again, and goes again, and comes back again, right? How many times? In principle, infinitely many times, yes. And so this process will be naturally modeled better as an autoregressive filter. Do you see this? It is just imagine me and the board to be the same object. If the board doesn't exist, this blackboard behind doesn't exist, and to produce the same infinite echoes, I will have to do what? I will have to speak out what the board would have reflected, which means I will have to speak, and infinitely many echoes myself of what I hear back. So I am speaking what I hear back. Do you understand the auto regression part of this? I am speaking what I hear. It's not me, it's this board. But what is actually happening is you are getting an infinite bounce using a structure that's automatically autoregressive. As a moving average structure, it's a convolution. Of course, it's linear and it's shift invariant. It's a convolution. As a moving average structure, it would require infinitely many coefficients for me to model it. As an autoregressive structure, it requires me only as many coefficients as there's the time, time of flight between the echo going all the way there and coming back. This makes sense or no? Here. I have this and then nothing, and something like this. Let's say I have this 1 and 0.1. And something gets spoken here. What will come out? If something gets spoken, the same thing will come out, then that will produce an echo. Right? There are actually, this is how echo machines work, by the way. Music industry uses it a lot. An echo machine. An echo machine works, what is it? It's an autoregressive filter actually. Okay? Akhercha ha tula dandavat, tula dandavat, tula. Have you heard this song? Some of you have heard this song. The infinitely many echoes, of course, they couldn't produce infinitely many, but the echoes are an autoregressive filter. So at that time they didn't have I'm told they didn't have an actual filter implementation because this recording is from the 1950s or something. So it was the singer actually, Lata Mangeshkar, it was the singer actually overdubbing the echoes, but nonetheless. Yes.
This can also have infinite dependencies on previous states, right?
Infinite dependencies on?
Previous states. Like you said that we can't use moving average because there will be infinitely many coefficients. This can also have infinitely many coefficients. Yes or no?
How?
I mean, it will rely on, it's basically relying on previous states, right? So there can be multiple echoes or infinitely many echoes.
If you have infinitely many echoes which do not start repeating after a time, then yes, you're in a problem. So it is true theoretically that ARMA filters are not all possible causal convolutions. So ARMA filters are just the computationally calculatable subset of causal filters, but nonetheless you use it to model any filter.
Maybe an intuitive answer would be that the coefficients are so small that it's okay even if we ignore them in the calculation.
Beyond the point, yes, yes. So it's an approximation. Okay, so this is a simplistic problem, but you know, a more realistic echo representation might have like multiple echoes happening. So in this room, for example, there would at least be 3 bouncing echoes. There would be many non-bouncing echoes, which are, you know, not between parallel walls. A lot of that is happening. And all of these complicated things are cascading and adding. So there are multiple parallel paths. There are multiple paths one after the other. So you are getting a lot of autoregressive and moving average filters, all cascading and adding together, which becomes a huge ARMA filter. So many a times an ARMA filter is a good approximation of real world systems. And we will study some methods of estimating ARMA filters. Okay? Do you understand this? This is going to be the last topic for today. Okay, so if you don't understand it, you always have the video to look it up. So let us say that I have the input and output recorded of some system which I want to estimate using an ARMA filter. Do you understand this? We already did this before for moving average filters. Correct? And that was called system identification problem, optimal system identification problem. Right? When we were doing Moore-Penrose pseudo-inverse, remember that? So we did that. If you know the input, you know the output, what is the filter that best explains this output coming from this input? Okay. Now we want to do that with ARMA filters. First step is you actually estimate a moving average filter. Okay. So take the input, take the output and estimate a moving average filter, but we are going to estimate a large moving average filter. Why? Because we want to actually capture the fact that these kinds of echoes or ringing structures have come up. We are not using ARMA, we are using a moving average estimate. So you do a large moving average estimate. Okay. So to just give you some numbers, let us say we were in this room and are trying to model this room. I am speaking, we are putting a microphone somewhere and we are trying to capture the system between these two. Okay. Now, let us say we did a recording for 5 minutes. Okay. It's a big recording. Okay. And from that, we will estimate a moving average filter between these two, which is say, let us say a 1 second moving average filter. A 1 second moving average filter is also a very large filter. Okay. Why 1 second? We are hoping that all the echoes die down within 1 second. If that doesn't use 2 seconds, 3 seconds, 10 seconds, it's still much shorter than 5 minutes, which means our estimation will be good. Remember, we need fewer coefficients than you have data so that the noise doesn't get estimated. So 10 seconds is still much shorter than 5 minutes, but it's still much longer, such that in the next step now we will use a very tiny number of ARMA coefficients to model this large number of moving average coefficients, right? Now these large number of moving average coefficients, now that you have them, you can say that, hey, what is this? This is a filter that given the input 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, produces these moving average coefficients, these step 1 moving average coefficients, correct? Yes? And this is the filter that I am going to estimate using a ARMA filter structure. Now my question is, I have a small ARMA filter structure, okay? something that looks like this. Correct? The question is, what are the best coefficients here to estimate or to come close to these coefficients such that this impulse input gives as close as possible to this output. Do you understand the point? And there are various techniques here.
Why can't we estimate AR and MA separately?
Why can't we estimate AR and MA separately? Because we don't have the numbers on this intermediate line.
So we can estimate MA. That estimate will give us those numbers.
No. So, this MA is a large MA which has not only the effects of the moving average, but has effects of the autoregressive filter as well. So the rings, the echoes, the infinitely many echoes are showing up in the moving average coefficients right now, because in this estimation no autoregression was used.
Yeah, I get that point.
Yes.
But if we can represent any filter as an ARMA, then even though there are MA factors which are getting estimated, that should be compensated in our. So you are basically saying that even though you are trying to estimate only the MA part of it, the AR part of coefficients is going to influence that, right?
MA part of it, the AR, what?
If we are going for moving average estimate, then auto-regression terms are there over there, which is going to cloud our estimate.
No. This MA estimate is not the part MA estimate at all. This is the impulse response estimate.
So this has both the components in it.
Yes. But don't call it clouding. It's supposed to be that way. There is no clouding here. This is the impulse response estimate. So now, one very simple method is as follows, is basically that you just look at what is happening here, okay. So now just think of this, 1 times this plus this times, no, just 1 times this is this output, but this you don't know. But now 1 times this plus this times this is this output, correct? 1 times this plus this times this plus this times this is this output. So I write down those equations. The unknowns are all of these numbers that you do not know. And you will see that these equations are linear in the unknowns. And so you get a number of linear equations in the unknowns. Okay. Now, one simple thing to do is just go on moving this structure. How many times? Till you have as many equations as you have these unknowns. And then you have as many linear equations as you have unknowns. You solve those linear equations, you will get these numbers out, and that is your ARMA representation. Okay. The noise reduction has already happened in this part, so this will give you a decent ARMA representation. This is called the Padé approximation method. Okay. I'll quickly just tell you the algorithms now. Okay, this is one method. Second method, so this method has one limitation, that you could have a lot of data in the impulse response, but you used only a little bit of it. How much did you use? As many as you have these ARMA coefficients. You used only that, and you disregarded the rest of the impulse response. So another method is as follows. if you look at this intermediate line, there will be some number here, correct? Then there will be some number here, then some number here, then some number here. But after the MA coefficients are all gone, what will happen after that? You will have zeros.
It's just the previous outputs carrying on. It's just the previous outputs that are carrying on, right?
It is just the
Previous outputs that
are carrying on here. But on this intermediate layer, you have zeros now. Because the moving average has gone past the 1. So now, from here onwards, you actually know the numbers in the intermediate layer. So now what you do is, you just look at these equations, and you have lots of these equations, and you have many, many more equations. Then you have those unknowns in the autoregressive part, and you solve this using what? Using best fit, using least squares, using the Moore-Penrose pseudo-inverse. Okay? And now that gives you a better representation of the autoregressive filter, because that is now going to give you all of these, the best representation of the ringing that is happening because of this filter, right? The infinite tail. Once you get that, you have this autoregressive filter, you take this and you just invert the autoregressive filter and get these numbers out. It won't work perfectly, you will have non-zeros here as well, and you have to disregard the other non-zeros. Just get these numbers out. This is called the Prony estimation method of ARMA filters. And we have just one final estimation method after this. Sorry, you are going to have to watch this video 10 times to actually get this out. These are very simple methods, but the way the textbook writes them is horrific, horrendous. So, okay, simple things are happening. And finally, third fellow said the following thing: let's do this thing like Prony did it. Okay? And then let us switch the autoregressive and moving average parts. We have already estimated the autoregressive part. We estimated the autoregressive part in this fashion, but now we switch them around, go to the type 2 representation, and then use the autoregressive part here. This will give you some result, and these numbers should remain the same, right? Because convolution remains the same. So these numbers will be the same as these numbers. Now you have a lot of numbers here, you have a lot of numbers here, you have an unknown moving average filter that you are trying to estimate. And how will you estimate that? Lot of numbers here, lot of numbers here, unknown moving average filter. How will you estimate it? Least squares, right? Moore-Penrose pseudo-inverse. This? Finally you can, but these are all heuristic methods, okay? These are not, none of these is optimal in any mathematical sense. These are heuristic methods. So this is called Shanks method or Shanks algorithm for estimating ARMA systems. Today, of course, you could attempt to directly use an ARMA filter here, have unknown coefficients, have data here, find coefficients that best fit this input to this output. How could you do it? You could do it using auto differentiation methods such as PyTorch, for example, or these kind of things, or TensorFlow. You could try to auto differentiate and see if you can get ARMA filters. I have never tried it, but of course these things will be slow. These textbook methods, even though they are old and heuristic, they are extremely fast methods. So they are still often used. All these ARMA system estimations are still being used daily in helicopters and airplanes, and all of these navigation systems are working on these kinds of techniques. So today we learned the W transform, which is actually the Z transform, its use in modeling or representing ARMA filters. We saw the beauty of ARMA filters, how ARMA filters remain ARMA filters in parallel addition, in cascading, and in inversion, and all kinds of combinations of these applications. We saw how to estimate real world systems as ARMA systems using these three techniques, and how calculation of all of that is easier using the W functional method. That's it for today. The last lecture is going to talk about the faster Fourier transform and some other such things, which means that eventually we are going to have covered, as I was telling to some of you, almost this entire textbook. Okay. Thank you very much. I'll see you next Thursday. Bye bye.